Allison V1710 was the only American-designed liquid-cooled engine to see combat in World War II. It powered 60% of U.S. Army pursuit aircraft, and it had one fatal flaw. It couldn't breathe, not at sea level. Down low, the Allison was a monster, smooth, reliable, cheap to build. But take it above 15,000 feet and it started to suffocate. The higher you went, the worse it got. And the air war over Europe, that was being fought at 25 to 30,000 feet. So America went to war with a fighter engine that ran out of air exactly where it needed to perform. This is the story of how that happened. How an engine that was genuinely good got stuck with a reputation it only half deserved. And how a British mathematician, a Rolls-Royce test pilot, and a polo-playing American diplomat ended up fixing a problem that should never have existed in the first place. To understand the Allison, you have to go back to 1929. The Allison Engine Company in Indianapolis had been around since 1915, originally building and maintaining race cars for the Indy 500. James Allison, the founder, was a co-founder of the Indianapolis Motor Speedway itself. After the First World War, the company shifted to aircraft engines, making its name refining surplus Liberty 512 engines and building propeller reduction gears. Then General Motors bought the company in 1929, and the new management had bigger plans. Norman Gilman, the general manager, sketched out a design for a brand new 12-cylinder engine, a V12, liquid-cooled, using ethylene glycol instead of water. The displacement was 1,710 cubic inches, 5.5-inch bore, 6-inch stroke. The U.S. Navy wanted it for their rigid airships, the Akron and the Macon. The Army Air Corps wanted it for a new generation of streamlined fighters and bombers. The name, by the way, comes straight from the military designation system. V for the cylinder layout, 1710 for the displacement. That's it. No marketing department involved. There was just one problem. The Great Depression hit, and funding dried up. Development crawled along through the early 1930s. The Navy's airships both crashed before the engine was ready. The Army didn't get its first V1710 until December 1932. And it wasn't until December 14, 1936, that the engine finally flew, bolted into a consolidated XA-11A test bed. We cover stories like this every week: the engineering, the people, the politics, the failures. If that's your thing and you're not subscribed yet, now would be a good time. All right, back to it. 7 years from first sketch to first flight. In aviation engine development, that's glacial. But the Allison team wasn't wasting that time. They were building something specific, something the Army Air Corps had told them to build, and that instruction would haunt the engine for the rest of its life. See, the Army had a theory. They believed the future of high-altitude engine performance belonged to the turbo-supercharger, not a mechanically driven supercharger bolted to the back of the engine like the British were developing. A separate unit powered by exhaust gases that could be mounted anywhere in the airframe. General Electric had been working on turbo-superchargers since the First World War and had decades of steam turbine experience to draw on. The Army was convinced this was the way forward. So when Allison designed the V1710, they built it with a single-stage, single-speed supercharger, just enough to get the fuel-air mixture into the cylinders at moderate altitudes. The plan was always that if you needed high-altitude performance, you'd bolt on a GE turbo-supercharger. The engine itself didn't need to do the heavy breathing. That was someone else's job. On paper, this made sense. In practice, it created a disaster. On April 23, 1937, the V1710 became the first engine of any type to pass the Army's new 150-hour type test at 1,000 horsepower. That was a genuine achievement. The engine was offered to aircraft manufacturers, and every major pursuit competition entrant in the late 1930s was designed around it. The Lockheed P-38, the Bell P-39, the Curtiss P-40. When the British Purchasing Commission asked North American Aviation to build P-40s under license in 1940, North American's Edgar Schmood said he could do better and designed the P-51 Mustang around the same Allison engine. So now you have 4 of America's most important fighters, all running on the same power plant. Over 70,000 V-1710s would eventually roll off the production line in Indianapolis between 1931 and 1948. 60% of all U.S. Army pursuit aircraft in the war carried an Allison. The engine had real strengths. It was built like a piece of GM industrial equipment. Modular design. You could swap propeller reduction gears, supercharger configurations, and accessory drives without redesigning the core engine. A single production line could build engines for fighters, bombers, everything. It was rugged, reliable. Pilots and mechanics loved it at low altitude. The V1710 ran smoothly at 1100 RPM. The Merlin needed 1600 just to idle comfortably. In the field, Allisons took punishment that would have killed other engines. Machine gun rounds through the cooling system. The Allison kept running. The Soviets, who received thousands of P-39s under Lend-Lease, swore by them. And the price was right. Allison could build these engines fast and cheap using American mass production techniques. No hand-fitting by individual craftsmen like the British Merlins required, just straightforward, repeatable manufacturing. But none of that mattered above 15,000 feet. Here's the physics. As an airplane climbs, the air gets thinner, less oxygen per cubic foot. A naturally aspirated engine loses power steadily as altitude increases because there's simply less air to mix with the fuel. A supercharger fixes this by compressing incoming air before it reaches the cylinders, maintaining sea-level pressure even at altitude. The better your supercharger, the higher you can go before the engine starts losing power. The Allison's single-stage, single-speed supercharger had a gear ratio that drove the impeller at about 8.8 times crankshaft speed. That was enough to maintain rated power up to around 11,800 feet. Above that, performance fell off a cliff. By 20,000 feet, the Allison-powered P-51A was doing 357 miles per hour. The Spitfire Mark V and the Messerschmitt 109F were both faster at that altitude, and they were getting faster. The original plan, remember, was turbo-supercharging, and it worked beautifully. In the P-38 Lightning, Kelly Johnson's twin-engine design had room for GE turbo-superchargers mounted behind each Allison in the twin booms. The results were exactly what the Army had hoped for. The P-38 was the first military airplane to exceed 400 miles per hour in level flight. At altitude, the turbocharged Allisons delivered. The P-38 shot down more Japanese aircraft in the Pacific than any other Army fighter. But there was a catch, actually several catches. The turbo-supercharger setup was physically enormous. All that exhaust ducting, the turbine, the wastegate, the intercooler plumbing. It worked in the P-38 because a twin-engine, twin-boom design had room for it. But in a single-engine fighter? The original XP-39 prototype had a turbo-supercharger. It performed well at altitude. Then the Army decided to remove it for the production version, partly to save weight, partly to make room for the unusual mid-engine layout. The production P-39 was stuck with the naked Allison and its single-stage blower. High-altitude performance was gutted. The British tested it, rejected it, and sent it back. The Soviets used it brilliantly, but only because the Eastern Front Air War was fought at low altitude where the Allison thrived. The P-40 had the same problem. No room for a turbo-supercharger, just the basic Allison with its anemic blower. It could fight. It did fight, all over North Africa, China, the Pacific, but it couldn't compete at the altitudes where the air war over Western Europe was being decided. And then the P-38 went to England, and things got ugly. The Western European air war meant long hours at 30,000 feet in temperatures that dropped to minus 40 degrees. The P-38's turbocharged Allisons started failing constantly. The manifold design delivered fuel and air unevenly across the 12 cylinders. Some cylinders ran lean, some ran rich. Detonation followed. The turbo-supercharger regulators froze in the extreme cold, getting stuck in either high boost or low boost mode. High boost caused detonation. Low boost meant one engine suddenly lost power, and a twin-engine fighter with uneven thrust starts fishtailing violently. The fuel made things worse. British fuel was blended differently than American fuel. The tetraethyl lead anti-knock compound separated from the fuel at extreme low temperatures and condensed inside the induction manifolds. This caused catastrophic detonation in random cylinders. The P-38 needed specific spark plugs for specific cylinders. It needed specially formulated fuel. It needed operating procedures that contradicted what pilots had been taught stateside, where instructors had them cruise at high RPM and low manifold pressure, exactly the opposite of what Allison and Lockheed recommended. General Jimmy Doolittle wrote a report to General Spaatz in January 1944, spelling out the failure patterns. By March 1944, when the first Allison-powered P-38s appeared over Berlin with the 55th Fighter Group, engine troubles had cut their effective force in half before they even reached the target. It was too late to fix the problems in the Allison or GE production lines. The P-38s were steadily pulled from bomber escort duty in Europe. By October 1944, they were gone from the 8th Air Force. Meanwhile, across the Atlantic, something else was happening, something that would change everything. In January 1938, a mathematician named Stanley Hooker walked into Rolls-Royce's factory in Derby, England. He had a doctorate in aerodynamics from Oxford. Ernest Hives, the production director, looked at his credentials and reportedly told him he was not much of an engineer. Hives hired him anyway. Hooker was given permission to study whatever interested him. He chose the supercharger on the Merlin engine. And what he found shocked him. The existing supercharger was running at about 68% efficiency. Through mathematical analysis of airflow, impeller blade design, and diffuser geometry, Hooker calculated that massive improvements were possible. He was right. His redesigned supercharger went into the Merlin-45, boosting power by 30%. The Spitfire Mark V got that engine. It became the most produced Spitfire variant of the entire war. But Hooker wasn't done. The Air Ministry wanted a high-altitude engine for the pressurized Wellington 6 bomber. They suggested turbocharging. Hooker said no. He designed a two-stage supercharger instead. Two impellers in series, with an intercooler between them to keep the compressed air from getting too hot. The first stage compressed the air, the second stage compressed it again. The intercooler, cooled by the aircraft's glycol system, kept charge temperatures manageable. The result was the Merlin-61, and it was a revelation. Now, understand what Hooker had done. The Allison's single-stage blower maintained rated power to about 12,000 feet. The Merlin-61's two-stage, two-speed supercharger maintained combat power past 25,000 feet. At 30,000 feet, the Merlin was still producing over 1,270 horsepower. The Allison, without its turbo-supercharger, was making maybe half that. The Merlin-61 went into the Spitfire Mark IX, which was suddenly 70 miles per hour faster at 30,000 feet than the Mark V. It could climb with the Focke-Wulf 190. It could fight at altitudes where the Allison-powered fighters were gasping. The two-speed gearbox was critical. At lower altitudes, the supercharger ran in low gear, providing boost without wasting power, spinning the impeller too fast. As the aircraft climbed and air got thinner, the system automatically shifted to high gear, spinning the impeller faster to maintain pressure. The Merlin's two-stage setup consumed 330 to 380 horsepower at 25,000 feet just to drive the supercharger. That sounds like a lot. It was a lot, but the power gained from all that compressed air more than compensated. Let's put the numbers side by side. The Allison V1710-39 and the Merlin-61 both produced roughly 1,570 horsepower at war emergency power near sea level, almost identical. At low altitude, there was nothing wrong with the Allison, but the Merlin-61 maintained 1,390 horsepower at 23,500 feet. The Allison was down to 1,150 horsepower at 11,800 feet. Same basic displacement, same general architecture, 12 cylinders, liquid-cooled, V configuration. The Merlin was 27 liters, the Allison was 28. The difference wasn't the engine, it was the breathing apparatus bolted to the back of it. And here's where it gets personal. In April 1942, Wing Commander Ian Campbell Ord was running the Air Fighting Development Unit at Duxford Aerodrome in England. He'd been testing a new American fighter, the Mustang Mark I, powered by an Allison V1710. At low altitude, it was astonishing. 30 miles per hour faster than a Spitfire Mark V at 5,000 feet, 35 miles per hour faster at 15,000 feet, and the Spitfire had a more powerful engine. The Mustang's advantage was pure aerodynamics. Edgar Schmood's laminar flow wing and that beautifully clean airframe produced less drag than anything else in the sky. But above 15,000 feet, the Mustang's performance fell apart. Campbell Ord was so impressed by the airframe's potential that he called Ronnie Harker, a test pilot from Rolls-Royce's flight test facility at Hucknall. On April 30, 1942, Harker took the Mustang up. 30 minutes later, he was back on the ground, simultaneously thrilled and frustrated. The airplane was spectacular. The engine was holding it back. Harker phoned Ray Dorey, head of Rolls-Royce's experimental division. How quickly could they fit a Merlin-61 into this thing? The Merlin was only 1 inch longer than the Allison. It could fit. There was no support at first. The Air Ministry in London didn't want to hear it. But Harker was persistent. He got to Air Chief Marshal Sir Wilfrid Freeman, who gave consent for a small test program. 5 Mustang airframes, Merlin 65 engines. The first one flew on October 13, 1942, with Rolls-Royce Chief Test Pilot Ronald Shepard at the controls. The results were not subtle. The Mustang X, as they called it, hit 433 miles per hour at 22,000 feet. The absolute ceiling was 40,600 feet. For comparison, the Allison Mustang topped out around 390 miles per hour at 15,000 feet and couldn't do much above 31,000. At 30,000 feet, the Merlin Mustang was nearly 100 miles per hour, faster than the Allison version. 100 miles per hour, same airframe, different lungs. On the American side, Lieutenant Colonel Thomas Hitchcock was paying attention. Hitchcock was the assistant air attaché at the U.S. Embassy in London, and he was one of the most remarkable figures of the war. A World War I veteran who'd flown with the French at 17. Shot down by the Germans, captured, escaped by jumping from a moving train and walking over 100 miles to Switzerland. After the war, he became one of the greatest polo players in history. Now he was in London, watching the test results come in and writing urgent reports to Washington. Hitchcock quoted Rolls-Royce's prediction that the Merlin would give the Mustang a top speed of 432 miles per hour. He lobbied relentlessly. There was resistance, serious resistance. Elements within the U.S. Army Air Forces, particularly on the production board, were actively hostile to British engine technology. The bureaucratic infighting cost months. Hitchcock didn't stop. North American aviation, meanwhile, had been thinking along the same lines. Under the company designation NA-101, they took 2 Mustang airframes, installed Packard-built Merlin 65s shipped from England, and redesignated the project XP-51B. The first one flew on November 30th, 1942, just weeks after the British Mustang X. At 29,800 feet, it made 440 miles per hour in level flight. The USAAF had already placed an order for 400 aircraft 3 months before that first flight. They could see what was coming. The conversion required some engineering. The Merlin 60 series was over 350 pounds heavier than the single-stage Allison, mostly due to the two-stage supercharger and intercooler. North American moved the wing slightly forward to correct the center of gravity. They replaced the 3-blade propeller with a 4-blade Hamilton standard unit to absorb the additional power. The distinctive chin-mounted air intake appeared, feeding the intercooler. The carburetor intake on top of the nose, a feature of the Allison installation, disappeared. Production of the P-51B started at Inglewood, California, in June 1943. The Dallas, Texas plant built the P-51C, same airplane, different factory. The Merlin Mustang entered combat in December 1943 with the 354th Fighter Group. It was immediately clear that the air war had changed. With drop tanks, the P-51 could escort B-17 and B-24 bombers all the way to Berlin and back. No other single-engine fighter could do this. The combination of Schmood's low-drag airframe and the Merlin's high-altitude power created something unprecedented. The 8th Air Force's bomber losses, which had reached catastrophic levels in late 1943, began to drop. The Luftwaffe now had to fight its way through long-range escort fighters that could match or beat anything Germany had at altitude. The Allison wasn't done, though. This is the part that doesn't get talked about enough. Allison knew the supercharger was the problem. Starting around 1943, they began bolting auxiliary superchargers to the engine in various configurations, creating what they called two-stage versions. The V1710-45 had a variable speed auxiliary supercharger. It produced 1,150 horsepower at 22,400 feet. Better. But fitting it into the Mustang would have required extensive airframe modifications and caused production delays nobody could afford. The auxiliary unit was too long. It lacked the intercooler and the refined two-speed gearing of the Merlin setup. It was, as one historian described it, essentially an afterthought, bolted onto an engine that was designed to work with an external turbo-supercharger that kept getting canceled from fighter installations. The P-63 King Cobra got some of these two-stage Allisons. They helped. But they never matched the Merlin's high-altitude capability because they lacked intercooling and the precision two-speed gear changes that Hooker's design provided. By war's end, Allison had pushed the V1710 to remarkable power levels. The final factory variant, the V1710-127, was designed to produce 2,900 horsepower at low altitude and 1,550 at 29,000 feet. It used turbo compounding, where exhaust turbines fed energy back into the crankshaft instead of driving a separate supercharger. It was static tested at 2,800 horsepower. It never flew. The war ended first. The last military application of the V1710 was the North American F-82 twin Mustang, which served in air defense roles into the early 1950s. The E, F, and G models used Allison G6 engines with an auxiliary supercharger. 375 of these final evolution Allisons were built in 1946 and 47. The last V1710 ever produced bore serial number A074125. So what went wrong? Or rather, what didn't go wrong? Because the real story is more complicated than the Allison was a bad engine. The Allison V1710 was not a bad engine. It was an engine built to a specification that assumed turbo-supercharging would solve the altitude problem. When turbo-supercharging couldn't be packaged into single-engine fighters, the engine was left exposed. The Army's decision to concentrate on GE turbo-superchargers rather than investing in mechanical supercharger development the way the British did, was the original sin. Until 1937, GE held a virtual monopoly on American supercharger knowledge. Allison, Pratt, and Whitney, and Wright all started developing their own superchargers around 1937 and 38, but they were years behind Rolls-Royce, where Hooker was already revolutionizing the field with mathematics the Americans hadn't applied yet. The irony is thick. The Allison's basic architecture could handle the power. The final variants proved that. 2,300 horsepower rated, 2,900 on test, the crankcase, the cylinders, the valve train, the cooling system, all of it was sound. The engine just never got the breathing apparatus it needed. At the time it needed it because the Army had bet on a different technological path. And it wasn't entirely the wrong bet. Turbo-supercharging worked spectacularly in the P-47 Thunderbolt, where the big Republic fighter had room in its massive fuselage for all the ducting. It worked in every heavy bomber the Americans built. It just didn't work reliably in the freezing cold at 30,000 feet over Germany when mated to a liquid-cooled V-12 in a twin-boom configuration. Too many variables, too many failure modes. The Packard Merlin, meanwhile, deserves its own kind of credit. Packard didn't just copy the Rolls-Royce blueprints, they improved the manufacturing process. They changed the crankshaft bearings from copper-lead to silver-lead alloy with indium plating, improving durability. They applied American mass production standards to an engine that had been hand-fitted by British craftsmen. 55,500 Packard Merlins rolled out of Building 81 in Detroit. The first complete engine came off the line on August 2, 1941. Today, the V1710 lives on in a small but devoted community. After the war, surplus Allisons flooded the market. Complete engines sold for as little as $200, $350 if you wanted a nice one. On a horsepower per dollar basis, there was nothing like it. Air racers snapped them up. The unlimited hydroplane racing community adopted them. The Arfons brothers from Akron, Ohio, stuffed Allisons into their Green Monster land speed cars. A guy named Jim Lytle in Southern California built a drag racer called Quad Al, with 4 V1710s on a 4-wheel drive chassis. There are about 4 shops in the United States that still know how to properly overhaul an Allison. The knowledge is fading. The engineers who designed it are gone now. But the engines keep running, in warbirds, in raceboats, in the hands of people who understand that this was never a bad engine. It was a good engine caught in a bad situation, built to a specification that assumed a future that didn't quite arrive the way anyone planned. The Merlin gets the glory. It earned it. But the Allison did 60% of America's fighter work in the biggest war in history. It did it at low altitude, in bad conditions, in theaters from North Africa to Burma to Alaska to the Soviet Union. Soviet aces scored more individual kills in P-39s than in any other American or British fighter type. That was the Allison, running smooth and reliable in the cold Russian air at the altitudes where the Eastern Front was fought. It just couldn't breathe up high. And in the skies over Western Europe, that was the only thing that mattered. And there you have it. The Allison V1710, the American engine that could do everything except the one thing the war demanded most. If you've ever seen one running in person, or you've got a family connection to any of the aircraft it powered, drop it in the comments. And if you made it this far, subscribe. We do this every week.